Oh, hi, college boy. How are you doing? Oh, you motherfucker. When you sit down to take the AP Physics test, they'll first give you this sheet with a bunch of equations on it. But where do these equations come from? And how do you even use them? Well, you're supposed to spend the last goddamn year figuring that out, but if you need a refresher then, look no further. I've divided this chart into two sections. In the middle gray area are universal expressions, definitions, units, Newton's laws. These things are true no matter what situation you're in. On the outside of this situation-specific formulas, which I'll explain in more detail later. That reminds me, these setups are not mutually exclusive. For example, you can have a tense rope dragging something along a rough surface, or if you're into some really kinky shit. We'll start off with the very first thing you learn in AP Physics, the derivatives of position. Now I know you're not supposed to call them that, but questions featuring these are so easy. They usually show up in graphical form, in which case, velocity and acceleration are just slopes, or position is just area, so don't be too intimidated. To our right here we have projectile motion, which I've labeled with a plus because it's not just projectile motion. Anything with constant acceleration follows the bottom two equations just fine. Projectile motion is just the most common form of it. It happens when your object is touching nothing but air and is near Earth's surface. And that's all of kinematics. Why did I list 1/2 as a physical constant? Okay, moving on. Forces are a bit trickier, but it's definitely worth memorizing them. Of course, the first one you'll encounter is the gravity force, but I'll get into that a bit later. The second one you come across is the normal force. Normal forces are all kinds of things, but the best way to think of them is that they stop objects from phasing into each other. These often come up in problems where they ask you what happens when some object loses contact with another, like a car going over a hill, for example. Next, we have the friction forces. These depend on the normal forces, but they appear in different situations. Kinetic friction only happens when there's sliding, and static friction is just, it shows up whenever it needs to show up. Static friction is also used a lot in limiting motion problems. For example, how hard can you pull on something before it starts sliding? But it can get pretty tricky because this is the only formula involving it. The next setup you're likely to encounter from forces are systems of objects moving together. To solve these kinds of problems, you have to remember that their accelerations are equal to, and their velocities are also equal, and then you can usually cough up some equations to get whatever you need. Ropes are also quite simple, but it's easy to confuse yourself and double count things. All you need to know is that the force from one end of the rope is the same strength as the force on the other end of the rope, just in the other direction. Ropes also show up in pulleys, so you have one object on a pulley and something else hanging off a ledge. For these problems, it's important to remember that the rope's length does not change. So if the object at one end moves, then the object at the other end also moves that same distance. Now we get to my favorite section of this chart, the purple area. In uniform circular motion, an object moves in a circle, and then it keeps moving in a circle, and then it keeps moving in a circle. Neither the speed nor the radius change, but we do have this neat little equation for the centripetal acceleration. If you have uniform circular motion, make sure to use a centripetal tangential coordinate system instead of the typical Cartesian one. Over here we have the universal gravitation formulas for force and energy. The equation sheet also lists the local gravity formulas, but just remember that the local gravity field is g times the mass of the Earth divided by distance from the center of the Earth squared, and height is just the distance to the center of the Earth, and everything works out. And speaking of energy, at the very center we have the holy grail of all of Physics 1, the work-energy theorem. This thing is so useful. There's a 60% chance you can just start with this and eventually figure out whatever your problem you're trying to solve. So I chose to put it here. This is also where power is introduced, but it never shows up ever, so that's why it's in red. The average velocity formula is in red because it's very dangerous. You'll almost never reliably be able to measure average velocity unless the acceleration is constant, in which case you just use the constant acceleration equations. I don't know, just avoid it whenever possible. If a structure has a green COE stamp, it means you can ditch the first step of the work energy equation and write EI equals EF, which, oh my gosh, it makes everything so much easier, and I love these problems. They sort themselves out really nicely. Next, we have collisions. In the physics world, these happen so fast that the forces between the objects barely have enough time to exert impulse on the objects, so we can kinda sorta say that the momentum of the system stays the same afterwards. In an elastic collision, the kinetic energy is also conserved, while in a completely inelastic collision, the objects stick together, which means that the final velocities of the two objects are the same, and that makes it a bit easier to solve. If the problem doesn't explicitly tell you that a collision is elastic or completely inelastic, then it's probably not either of those things. And rotation is AIDS, so good luck, I guess. Just make sure to not just assume everything is rolling without slipping, because that will screw you over a lot. And also look at all these fuck-ass formulas, I guess. I don't really know. Our yellow section here contains oscillating systems. Not much to say about these. The derivations of some of these formulas are quite annoying, but don't worry about any of that. Pendulums conserve energy because the tension force from the rope doesn't do any work. It's perpendicular to the motion. And that reminds me, if you have a spring setup, make sure to include both the thing on the spring and the spring itself in your system. And if you have gravitation, make sure you include both objects. So include the earth and whatever is falling towards it in your system, for example. Okay, cool. The pendulum formulas only work out for small path angles because the sine of the angle has to be somewhat close to its measure in radians for everything to work out. It should be pretty obvious when this is or isn't the case, though. Last but not least, we have fluids, which are strange. You have to analyze them either as little chunks moving together or as some very large object acting uniformly across the surface. They're weird, and they were just added to the AP Physics 1 curriculum, so this didn't need to happen. This is also why pressure is useful. In a continuous flow, the amount of fluid coming into this section of the problem is equal to the amount coming out. This flow rate can be rewritten as the cross-sectional area of whatever section of fluid times its velocity, but it's also equivalent to volume per unit time. This means that in narrower sections, your fluid will be moving faster. For objects submerged in the fluid, the pressure at the bottom is way larger than the pressure at the top of the fluid. This creates a buoyant force to the surface of the fluid. It's equal to the weight of volume displaced. You know this. You learned this in like elementary school. Just remember where it comes from. Lastly, we have a distinction to make. Bernoulli's principle, which is that in any flow, higher speed means lower pressure, and lower pressure is where the fluid is moving faster, is always true. This is why airplane wings work. The air moving above the wing has to speed up, and this means the pressure pushing down on the top of the wing is smaller than the pressure pushing up from the bottom of it, and this creates a net force upwards, generating lift. But if you want to be more specific, then in a specifically continuous flow of an incompressible fluid, so like the example over here, we have this beautiful formula. Don't worry about how it's derived, I couldn't figure it out either. It can be seen as an extension from the hydrostatic pressure equation, which is just this when velocity is 0. And we're done. Good luck on the test this Wednesday, and if I made any mistakes, my bad, bitch.